Hello everyone. Today we are going to talk about balancing chemical equations. And balancing these chemical equations is a pretty simple concept. It really only requires you to understand one major concept, and that major concept is going to be conservation of matter. So really, when you're balancing chemical equations, the only real thing you have to keep in mind at all times is that you have to conserve matter. So what does that mean? What that really means is that all of the elements that you find on one side of the equation, so in this case, let's talk about the left side of the equation. On the left side of the equation, you can see that there's calcium, oxygen, hydrogen, and phosphorus. Well, the same elements and the same quantities of each element must be found on the right side of the equation. So immediately when you see a reaction, you need to determine if that reaction is balanced. So in this case, we're going to look and see if the reaction is balanced by just looking at one specific element and counting it up. So let's look specifically at calcium. So here you can see that there is one calcium, and on the other side of the reaction, on the other side of this arrow right here, you can see that there are actually three calciums. So immediately we know that the reaction is not balanced. So when you're learning to balance reactions, what I recommend is that you list out all of the elements in the reaction on both the left and the right side and the quantity of each one involved. So here we can see that on the left and right side you have calcium, oxygen, hydrogen, and phosphorus, right? So, and that is the same thing on the right side as well. Oxygen, hydrogen, phosphorus. So what I recommend you doing is now listing out the number of each. So here we can see we have one calcium. On this side we have three calciums. On this side we have, so here you see that there's one oxygen, but there's a 2 here because it's in the hydroxide species. So that means that there's 2 oxygens right here. And then you can see in the phosphate that there are actually 4 oxygens. So 2 plus 4 is going to be a total of 6 oxygens. Likewise, on this side, there's 1 oxygen and water. And then there are 2 phosphates, and each phosphate has 4 oxygens. So there's a total of 8 oxygens in the calcium phosphate and 1 from water. So you have a total of 9 oxygens. And then for hydrogen, we have 1 from the hydroxide, and there are 2 hydroxides, so there are 2 hydrogens, and once again there are 4 oxygens in the phosphate, so you have a total of 6. Oh, I'm sorry, I did oxygen in that case instead of oh, my mistake. So you still have 2 hydrogens in calcium hydroxide, but then there are 3 hydrogens in the phosphoric acid. So this will be a total of 5. That's my mistake, I'm sorry. And then for phosphorus, there is only 1 phosphorus on this side of the equation. So here we have 2 hydrogens, no hydrogens here, so we just have a 2. And once again, there are 2 phosphates, and then there is 1 phosphorus for each phosphate, so you have a total of 2. Okay, so when you're going about balancing an equation that's non-trivial, sort of like this one is, you should try to make an educated guess as to how to balance the equation. So for me, I immediately noticed that you have a calcium, 1 calcium in calcium hydroxide, and 1 phosphorus in phosphoric acid, right? But then on the other side of the equation, you have calcium phosphate, right? So calcium and phosphorus on that side are connected, whereas on the reactant side, they are both independent of each other. So for me, I would try to balance calcium and phosphorus first on the reactant side, and then try to balance oxygen and hydrogen through the water on the reactant side, on the product side. So let's do that, right? So you have 3 calciums on the product side. So let's just put a 3 here, and now we'll have 3 calciums, right? So that will change the number of oxygens and hydrogens we have. So here we'll now have 2 oxygens times 3, which is going to be 6, plus the 4 we already had, which is going to be 10 total. For hydrogen, it'll be the 2 hydrogens times 3 plus the 3 we already had, so that will go to 9. And then the number of phosphorus doesn't change, right? So now we have calcium balanced. So the next thing I'm going to look at is the number of phosphorus we have, right? So here there are 2 phosphorus on this side, only 1 phosphorus on this side. So I'm going to put a 2 here, right? So the number of calciums we have will not change. It'll still remain 3. The number of oxygens we have, well, we'll still have 6 from the calcium hydroxide. But regarding this one, we will now have a total of 8, right? So you'll have 4 oxygens from the phosphate, and then 2 from the stoichiometric, or there's 2 phosphoric acids from the stoichiometric coefficient. So that'll be 8 oxygens in total, plus the 6 you have, that's going to total to 14 oxygens. So for hydrogen, we will now have the stoichiometric coefficient times the 3 hydrogens you have from the phosphoric acid, resulting in 6, plus the 6 you have from calcium hydroxide. So that'll be a total of 12 hydrogens. Then we already know that the phosphoruses have doubled because you have 2 moles of the phosphoric acid, so now you're going to have 2. So now both on the reactant and the product side, calcium and phosphorus are balanced. So what's convenient about this is now you only have oxygen, hydrogen not balanced, but there's water right here, and water has neither calcium or phosphorus in it, so you can just use this water to balance the number of hydrogen and oxygens left, right? So here we can see we have 12 hydrogens and we have 2 hydrogens on this side. So if we just put a 6 here, we now can say that we have still 3 calciums. So we'll have 6 oxygens from water, and then we will have the 8 oxygens from calcium phosphate. So that'll be 14 oxygen. You have 2 hydrogens times 6, which is going to end up being 12. And then you still have 2 phosphorus. So now this equation is actually balanced. And this is probably the best way to balance equations when you're first starting out. And as you do it a few times, it becomes actually very trivial to you, and you're able to intuitively see it more frequently. So let's do one more example. So in this case, we're going to be reacting iron oxide with nitric acid to form iron nitrate and water. So let's set it up the same way we did before. So this divides the 2 sides of the reaction, the reactants and the products. And here we have iron, we have oxygen, we have hydrogen, and we have nitrogen. So on the reactant side, you can see we have 2 irons, we have 3 oxygens from the iron oxide, and 3 oxygens from the nitric acid, which is going to give us a total of 6 oxygens. We're going to have 1 hydrogen, and we are going to have 1 nitrogen. Let's do the same thing on the other side, because we have conservation of matter, so we are not destroying any of the elements, so they are the same on both sides. So here we have 1 iron, we have 3 nitrates, right? And then there are 3 oxygens per nitrate, so that's 9. And then we have 1 from the water itself, so that's going to be a total of 10. We have no hydrogens in the iron nitrate, but we have 2 hydrogens in water. And now we have 3 nitrates and 1 nitrogen in each nitrate, which is going to total to 3. So immediately, again, we can see that the number of all of the elements are different on both sides of the equation, so this equation isn't balanced. So what we're going to do is make an educated guess again. So here we can see that iron and nitrogen both are together on this side, and there's a different number of irons and nitrogens on the reactant side than the product. And you can see iron and nitrogen on the reactant side are not in the same molecules. So let's try balancing them again. So here we know we have 2 irons, and here we know we have 1 nitrogen, but here we have 3 nitrogens and 1 iron. So let's try balancing the number of iron atoms on this side by putting a 2 in front of iron nitrate, right? So let's do 2. That changes the number of oxygens, so now you have the 9, like we said before, from here, times 2, which is 18, plus 1, 19. Number of hydrogens doesn't change. And now we have 3 nitrogens times 2, which is going to go to 6. Okay, so now we have more nitrogens, or we already had more nitrogens on the product side than the reactant side, right? So let's try balancing the number of nitrogens. So if we add a 6 here, right, this doesn't change the number of iron atoms we have. It changes the number of oxygens. So we have 3 from iron oxide. Now we have 3 times 6, which is 18, plus 3, 21. Changes the number of hydrogens to 6, and it changes the number of nitrogens to 6 as well. So now we have iron and nitrogen balanced on both sides. So what's convenient once again about this is that we have a water to balance the number of hydrogens and oxygens on both sides. You can see on the reactant side you have more hydrogen and oxygen than you do on the product side. So to balance them, what we'll do is we'll put a 3 in front of water. This will leave the number of irons the same. It'll change the number of oxygens. So here we have 3 times 3, which is 9, times 2 is 18, plus 3 is 21. And then we'll do hydrogen. So we now have 3 times 2, which is going to be 6. And it did not change the number of nitrogens we had, which is also going to remain 6. So now we have effectively balanced this equation. So as you can see, balancing equations is actually very simple. It just takes a little bit of practice, and it's pretty much just counting and multiplying. I hope you enjoyed the video, and I hope you learned something. Stay tuned for the next one.